All right, the third speaker for the first session is Amin Vahdat. He received his PhD in the Now project, also in the 90s, right? Yes, mid-90s. He had a distinguished academic career in Duke and San Diego, and he's been at Google for a few years now, where he is a fellow and the technical lead for networking. He had a tremendous impact on data center network, and he'll tell us a lot about this. Here's Amin telling us about the future of networking.
Okay, it's a real pleasure to be with you all here today. I spent 9 years here at Berkeley as an undergraduate and as a graduate student. In all sincerity, I equate nothing more with UC Berkeley than Dave Patterson, so that's one of the principal reasons why I'm so happy to be here. I promise, talk about networking, but I'm going to take advantage of standing before you in front of this bully pulpit to give a couple of anecdotes about Dave. He's been a real inspiration to me throughout the years. Yes, about systems design. I mean, the principles of letting analysis, data guide what you do, and letting the trend be your friend seems obvious to many perhaps sitting in this audience, but it's the one that's probably hard won and not popular enough in the academic community, I would say. But beyond systems design, I actually often find myself thinking, what would Dave do in many, many different kinds of situations? So let me give you two examples that have come up. One is always being willing and able to learn something new. I actually, on the Now project, worked on operating systems. I was an operating systems graduate student. I showed up my first day, assistant professor on the new job, and they said, Amin, congratulations, you need to teach networking. So I don't know anything about networking. I'm an operating systems person. Well, I said, you're as close as we got. Everyone wants to take networking. We have someone to teach operating systems. So I bought the textbook. I read it the day before, usually showing up to class, and I showed up super enthusiastic every day. Boy, let me tell you what I learned about networking, folks. That has served me well, I think, over the years. On a different note, I have somebody working for me, fantastic, insightful, super bright, always has the right technical sort of assessments. In person, always great, still could not write an email to save his life. Always would come off wrong, sometimes come off mean, sarcastic, etc. He got his PhD in computer architecture, his advisor sitting in this room, and I actually sent him an email. I said, I want you to write every email like you're writing it to Dave Patterson. and he is a man transformed. It is a true story. So thank you, Dave, for lessons on many, many fronts, being willing to learn new things, treating everyone with respect, and being someone who I could invoke to get the right level of respect out of the folks. Okay, so with that, let's talk about networking. It's actually a super exciting time to be in networking. And networking, of course, to me is an enabler for computing. So computing is at what I think is a once-in-a-generation sort of shift. We're at the beginning of it, but I think we're past the tipping point. Being biased, I think the last one happened around the Network of Workstations project, moving toward PCs, workstations, commodity parts to deliver capacity, compute capacity. We're now past that 20-year trend and moving toward the next one. So I'll begin with talking about computing and talk about how networking, again in my biased opinion, is going to be playing a very important role in defining what computing will look like over the coming 20 years. So computing is at a crossroads. I think that if you were to transport an undergraduate back in time today to about 20, 25 years ago when I took my undergraduate distributed programming course, distributed systems course, that undergraduate wouldn't be so shocked. They wouldn't feel out of place. They wouldn't think, hey, this is so arcane. And this is to say that despite literally a factor of 10,000 improvements in computing and networking performance, the way we're building distributed systems is mostly unchanged. In fact, what we've done is we've layered more and more, let's say, cruft on top of the baseline hardware such that we're certainly not delivering a factor 10,000 difference in performance, given that the underlying hardware supports it. At the same time, the free lunch in performance improvements is over. I mean, many of you remember the good days not too long ago when all you had to do was wait 18 months and your code, unrecompiled, would run twice as fast. Those were good times. Those days are also over. We had a great talk from Garth. I think we'll be hearing more about this. Storage capacity has increased dramatically, but the I/O latency gaps continues to be there in a big way. We've actually been assisted that to date, we've had this stubbornly slow 10 millisecond access time for disk. And the reason that's been good for us is that we've been able to disaggregate disk. We can, at the level of an entire building, make all the disks look like they're local to your computation. 10 milliseconds is an eternity. With this new generation of storage devices that are coming along, the networking and compute communities are no longer going to have that luxury of being able to deal with 10 millisecond devices anymore. And that's going to require some new architectures moving forward. Okay, so that's one big trend in computing, as Dave mentioned, and we're not going to argue with Dave today. The cloud is the future, but let's talk for a moment about what that future might look like. First, let's go back about 10 years with the emergence of the cloud, what I'll call Cloud 1.0. Here, for enterprises building their own private data centers, virtualization allowed us to reap substantial capital expenditure savings. What I mean by that is that you could take workloads that used to run on, say, 100 servers and multiplex them down, collapse them down onto 10. Right? They could get their own operating system image, their own configuration. They would run isolated from one another, and this was a big win. Where we are today, I'll call Cloud 2.0, we can now largely outsource the construction of the hardware that it takes to run our computing workloads. We know that it takes substantial expertise to build efficient hardware infrastructure, data centers. I mean, basically, the large providers of computing infrastructure can do it from a power, cooling, commodities of scale perspective, 2x, 3x more efficiently than smaller deployments. You also get just the right amount of hardware on demand. So you don't have to buy for the max that you need. You can basically pay for what you need at any given point in time. And this has also been great. At the same time, the compute model is the same. How you configure your systems is exactly the same. You pick what operating system you want, which patches you need to apply. You figure out how many instances of your web server you need, your database you need. How are you going to do load balancing across them? How are you going to schedule things in different places? I could go on and on and on. The bottom line is that how we do computing hasn't changed. It is true that we now have the benefit of not having to build our own hardware infrastructure, and that is a big win. Where I think we're going is Cloud 3.0. And here, the notion is to be able to focus on compute, not on servers. And it doesn't matter if those servers are virtual or real. We need to move away from having to think about having servers. So we need to move to a model with serverless compute, not on where our data is placed, how we're going to do load balancing among different servers, how we're going to patch the operating system, what our security policy is for access control to individual servers, et cetera. We need to be able to focus on writing our application and having it scale out, scale up, down, et cetera, rather than on configuring the low-level hardware. So from a networking perspective, we should be aiming for Cloud 3.0. We, in the networking community, I think, are pretty stubbornly also stuck with taking stuff that we know from private clouds and bringing them into public clouds. So now, rather than having a firewall that's a physical box that you buy, you get to buy a virtual firewall. You get to buy a virtual load balancer. And I'm not sure that's real progress from the perspective of realizing the future of computing. Okay, so let's take it back to networking and Cloud 3.0. Given the direction that I think we need to be going, what are some of the things that networking can be doing? Storage disaggregation, we talked about this. I think we've been largely successful with disk. Right? So we have all these bytes. Most of them are never accessed. That's good. When they are accessed, we have 10 milliseconds minimum, and often more with some queuing, et cetera, to access it. So the network, especially within the data center, can get to it. But with the new storage technologies that are here today, flash and next generation NVM, we're not going to have the luxury of dealing with pretty slow storage devices any longer. What's the network need to do to keep up with that? I'll go into some detail about that moving forward. Transparent live migration. So the idea here is that you don't want to be thinking about your operating system needing to be upgraded and patched. Even though I started in operating systems, I would argue that most people don't want to be thinking about the fact that they have an operating system. Underneath the hoods, this is going to still have to happen. There will be operating systems. They're going to have to get patched. What transparent live migration means is that your compute moves from one physical server to another without you even noticing, and no downtime. Now imagine that you have a compute instance with potentially hundreds of gigabytes of state, accessing terabytes, maybe even petabytes of storage. It will take a pretty intricate and pretty fast network to enable you to move that state with hundreds of gigabytes from one physical place in your data center to another with no downtime, no notice, and basically full availability. Seamless telemetry. Here, again, what you should be doing is getting information about how well your service is delivering, say, requests to end users, not on very low-level metrics that allow you to do load balancing decisions and placement decisions. And finally, an open marketplace. We talked about App Store. I believe that we need something similar for the cloud. You should be able to essentially buy and instantiate the equivalent of an NFS server in your computing environment with a click of a button. And that NFS server should be configured, seamlessly accessed, secure, et cetera, with all the right credentials and keys and data access without you having to figure out how to go and change every router, every switch. Okay, there might be virtual routers and virtual switches, but there's still routers and switches. All those should be going away. Okay, so to put this back up one level, in Cloud 3.0, the network should be delivering applications, not virtual machines. You shouldn't be thinking about machines, virtual or otherwise. We should be focusing on policy, what your security policy is. In other words, who has access to what data, rather than how you configure your middle boxes and how you make sure that your packets flow through the right middle boxes to enforce security rules and the like. Actionable intelligence and even machine learning, you shouldn't have to have pre-canned queries about what your system looks like and how it's evolving, et cetera. You should have help with that, and you should actually be getting insight into the behavior of your data without necessarily knowing exactly how to formulate the right SQL query. And finally, you should be thinking in terms of service level objectives, SLOs. Basically, what's your availability target? What is your latency target? Not on placement, load balancing, and scheduling of underlying servers. Okay, so all this is going to take a neat trick. It's going to take the trick of at least providing the illusion that the network has disappeared. And one path that we've been following for this is using software-defined networking to make the network more manageable, more scalable, and much less apparent from the perspective of the applications running on top of them. So I'm going to give a few examples of this through Google's experience. Okay, so compute is taking place in these very large data centers. Here's one picture. Essentially think of this as a building, tens of megawatts of power with tens of thousands of servers. Google's mission, going back to the origin of the company, was to organize and remains to organize the world's information and make it universally useful and accessible. All the world's information is pretty big, and it's growing really fast. So it was far beyond the capacity of any single server or tens of servers or hundreds of servers to go get at this data, process it, make it useful and accessible. So by necessity, we developed a fair number of pieces of distributed computing infrastructure to go through this data, starting with GFS, the Google File System, in 2002, through systems like MapReduce, Bigtable, and most recently things like Spanner that perhaps for the first time show how to provide consistent data replicated across the planet. In all these cases, as I'll draw upon in a moment, the common thread was we're going to have logically centralized control over the data and compute of an entire building. And this ran really counter to the notions in industry prior to this time. Right? Can you think of all the disks in a building as constituting one big file system? Can you basically plug disks in and out as you see fit, servers in and out as you see fit, and the file system grows and shrinks underneath the hoods from the perspective of the applications that are accessing it, without them knowing, without them having any downtime, any data migration, et cetera. As new technology becomes available, it also becomes transparently available and accessible to the applications. Okay, all this innovation in distributed computing underneath the hoods was delivering and requiring just sort of huge growth in data center network bandwidth requirements. This is just one illustrative example that I have on this chart here. It's over about a 6-year period, and it shows the aggregate growth in data center network bandwidth over that time period. And the takeaway is that over the 6-year period, we had a 50x growth. Actually a little bit less than 6 years, 50x growth in data center network bandwidth. We couldn't buy for any price a network that could meet the demands of our distributed computing infrastructure. So what we had to be doing at the same time was developing network technologies that could keep pace with our distributed computing infrastructure. And here's just a set of examples. I, again, won't spend time on most of them, but we had to, for example, build our own content distribution network to deliver videos, let's say, across the planet. Watchtower, Jupyter, I'll talk about in more detail, our own data center network infrastructure. We built our own private wide area network to connect the data centers together called B4, etc. All of these, in one form or another, use the notion of software-defined networking. And so, and they used software-defined networking before we had the term to describe what we meant. But the basic idea is, and really counter to how networking worked prior, is to leverage logically centralized control of all the networking elements, either within a building or across the planet, to provide the illusion of one big network that provides connectivity from port to port and enforces policy. Now, how that's realized, which switch, which middle box, which firewall, which load balancer, ideally, and we're not to the ideal yet to be clear, but ideally, you don't know and you don't care. The logically centralized controllers know what policy you're trying to get at with respect to connectivity, what the bandwidth requirements are, and it delivers it. As new networking technologies, pieces of hardware become available, you plug it in, and rather than discovering by pairwise message exchange with neighbors what role those elements should be playing in the network, they're told. So one of the reasons I actually fell in love with networking was the beauty and the challenge of the protocols involved. I mean, the notion that you could have a network element in the internet come up without knowing anything, exchange some messages with its neighbors, and then become a fully functioning member of this global community of forwarding elements was to me really, really beautiful. And yet it's a really, really hard problem, and perhaps an impossible one to solve. Think similarly in terms of congestion control. We have this amazing protocol, TCP, that without any state figures out exactly what its fair share of global bandwidth is, and relearns it continuously. I mean, this is, to me, again, a stunning achievement. But in both cases, we're solving really hard problems that are much easier to solve if you have a central entity that knows what the network looks like, what it should look like, and enforces that policy. That's really what SDN is about. Take the brains out of the individual elements, have a blueprint for what the network looks like, and continuously enforce that. Okay, so let me get to storage and computes. So let's shift gears a little bit. What kind of network did we need to support our computing needs within the building? And what I'm going to argue is that you need a balanced infrastructure, compute infrastructure, and it needs to be running at building scale. Why balanced? So you've got CPU, you've got disk, you've got flash, you've got RAM, you've got network. You have to keep all these things in balance for your computation to run effectively. If some resource is scarce, one of these 5, let's say, you're limiting the value that your data center can deliver. Similarly, while other resources are sitting idle because of that one scarce resource, you're increasing your cost. And of course, both are bad. So that's the argument for balance. Now, what about scale? What we found is that you actually benefit substantially from running your computation, even if each individual computation is moderate in size, maybe 100 servers, maybe 50 servers, maybe 200 servers. You get substantial efficiency wins of having a big domain to schedule across. So here's the intuition. Imagine you have a series of jobs arriving, and you can either schedule them in their entirety across 10 1,000 server clusters, or the same set of jobs can be scheduled in one 10,000 server cluster. Without going through the details, hopefully you can convince yourself that because of bin packing, you'll get substantially more efficiency. In our studies, perhaps 30% or more by having those larger scheduling domain, even for the same set of jobs. Okay, so scale matters. and balance matters. How do we build a balanced data center? Here I'm going to go back to perhaps even before Dave started his career here at Berkeley, to Amdahl's lesser-known law for systems balance. And this says that you need a megabit per second of I/O for every megahertz of computation in parallel computing. Let's see how that plays out in one of our prototypical buildings. Let's say I have a building with 50,000 servers. That's not an unreasonable sized building today, tens of megawatts. And let's say I fill this building with a number of servers, 50,000 servers. Each has 64 cores, 2.5 gigahertz each core. Fortunately, I'm not a computer architect, so I'm going to multiply 64 times 2.5 gigahertz, and we're going to determine the bandwidth requirements of each of these servers to be about 100 gigabits per second according to Amdahl's law. All I/O is remote, right? We don't want to have I/O local because we wind up stranding a whole bunch of resources. So flash, think of a flash device as supporting 100,000 IOPS per second with 100 microsecond of access latency, right? That's 2 orders of magnitude better than disk. Non-volatile memory coming soon, finally, in the next year or so, is going to deliver 1 million plus IOPS with 10 microsecond access latency. 1 million 4 kilobyte IOPS, that's about 40 gigabits per second of bandwidth. So that saturates just about saturates one of these 100 gigabit per second links. Certainly if you want access to 2 non-volatile memory devices, you've saturated one of those links. So doing the math, 50,000 servers, each needing 100 gigabits per second at least, according to Amdahl's rule of thumb, you wind up with the need for a 5 petabit per second network in each of your buildings. Now maybe I'm wildly exaggerating the bandwidth requirements, and some would say I am. Let's say we need a 10 to 1 oversubscription ratio, so you only need a tenth of that, 500 terabits per second. If you cut the internet, capital I internet, in half, the entire bisection bandwidth of the capital I internet is substantially less than 500 terabits per second. So now we have this network need that is more than the size of the entire internet, and we have to put it into every single building that we're deploying for computation. Okay, and latency, of course, is now key. I've got these 50,000 servers, and I want to make NVM be a building level resource. For it to really be a building level resource, you can't make it too slow. Okay, with a 10 millisecond disk, it's hard for the network to make it too slow. With a 10 microsecond NVM device, it's really easy for the network to make it too slow, right? If I've got this awesome 10 microsecond latency device in the data center, it's pretty easy with queuing and everything else to, at the tail, add a millisecond of latency. And certainly trivial to add 100 microseconds of latency. So now I've made it maybe 10 times, perhaps 100 times worse. And now all of a sudden I'm not so excited about disaggregating it, right? I stick it into each server and access it locally. But now we've gone backwards, limiting our value because we can't build balance. Okay, availability I'll go through quickly. We're evolving the network all the time, and we've got to be able to do so without taking down the tens of megawatts of infrastructure. So I think for me the main takeaway here is that from a Cloud 3.0 perspective, from a disaggregation perspective, from the perspective of blurring the lines between individual servers moving forward, the network is going to be playing a disproportionately large role in defining the future of what computing means. And that's one of the main reasons why I continue to be very excited to be working on networking. Since Christos is already standing up and he's going to step up the stairs pretty soon, I'll skip the details of how we built our network. We actually have papers published on this, so you can get probably more detail than you like. But I will wind up here to show you, actually right here, that our latest generation of Jupyter network actually scales to 1.3 petabits per second per deployment. So right in that 500 terabit to 5 petabit range. And I'll reveal not so big secret that we're talking about our 2012 technology here in Jupyter, not necessarily what we're doing today. So these bandwidth demands are real in the data center, and they're continuing to grow at substantial rates. We've applied these same ideas to our WAN, to our network virtualization infrastructure, B4 and Andromeda. Okay, so I'll conclude here that we need to continue to work hard at making the network disappear, logically centralized control, in addition to merchant silicon, cloud topologies, and the centralized configuration is a pretty compelling way to get there. Okay. With that, I'll stop and take questions.
Questions?
Yeah. What impact do you see ManyCore having on this networking scene as we start to get up to, say, having, 100 cores on a die?
So this is happening today. And essentially the notion here is that the 100 gigabit per second, let's say, bandwidth requirements of individual servers is not driven by any single core. And in fact, I'd argue that basically no core running at 2.5 gigahertz really cares about that level of bandwidth. It's really the multiplexing of hundreds, thousands, perhaps tens of thousands of individual, relatively small flows that are driving the bandwidth needs from every server.
Hi, Dave Edstrom with Mimics. Great talk. I'm curious, you didn't mention or I didn't catch very much about security or encryption with networking, and I was wondering about your thoughts about the Feinstein-Burr Compliance with Court Orders Act, and if it goes in the wrong direction, what are Google's thoughts, I guess, on that?
So I'm going to punt on the second question just because I'm not qualified to speak to Google's thoughts on the policy questions, and I'm not saying that to dodge. I'm not the right person to speak for Google in that context. And I will ask the more general question in terms of security and encryption requirements. It is a huge driver for our network architecture overall. And what I'll say is that since the beginning of time, Google has been a big target for attack. We're constantly under attack. And it's always, it's never a question of, hey, is there an attack happening? It's how big and scary is the attack? And some of them get really big and scary. And it's gotten bigger and scarier as we've become a public cloud provider. So it's a big, big issue. I didn't talk about it in detail, but certainly it's a driver.
So you talked a lot about about Amdahl's lesser-known law, which actually we knew about 30 years ago because Dave told us. Yeah. But
that's why I included it.
Yeah, there you go. But what I'm wondering though is that there's been a big trend to trying to move the computation to the data. And your comment was, well, all of our storage is away from the compute nodes. How would this requirement, this demand drop if you were to be more intelligent, or could you be more intelligent about placing the computation so you didn't have to move data all over the place like you do now?
So I don't know about the trend. I'm not sure I agree with the trend. I guess we can do a pretty good job building general purpose compute infrastructure, and having a fungible pool of that across a building is pretty nice. What I will say, and I'm glad you asked the question, is wouldn't it be great to have these hardware devices be built from the ground up to be network citizens? And right now, we have to sort of retrofit them on our own to make them be network citizens. Even for disks, okay, it was easy with disks, 10 milliseconds. But at the 100 microsecond and 10 microsecond level, we're having to do a lot of work to make them first-class citizens.
More questions?
So I noticed you had a closed network.
The private wide area network, yes.
That was originally invented by the phone company. Can you say a little bit about why you're returning to that topology?
Closed topology. Oh, yes. It was actually, it's a 60-year-old topology, as you note, and many of the good ideas, perhaps all of them in networking, did start in the phone company, so I feel no remorse in taking yet another one. But the origin was building a non-blocking network technology. So remember, we need to get to, let's say, 5 petabits per second. The state of the art prior to us starting down this path was to buy 4 of the biggest switches that you could buy from non-phone company vendors and stick them into your data center. Buying a bunch of small switches and arranging them appropriately in a CLO topology turned out to be a great way to deliver non-blocking technology affordably.
Amin, Rick McGear from US Ignite. Over the years, a lot of us have been extremely excited at the promise of software-defined networking. And I think it's fair to say that most people who have tried to use it haven't been nearly as successful as Google. And Google's been outstandingly successful with it. Can you speculate as to why that is? Why Google has done so well when others have done less well?
It's a great question. I think that one reason, honestly, is that when we started down the path, we had a bunch of people, and this was before I got to Google, to be perfectly clear. We had a bunch of people who came from a distributed computing background and tried to solve a networking problem. That's part one. Part two, we had two rather large, spectacular failures that never saw the light of day. And they were on the slides, they're in the paper. The company was willing to stick by the approach, despite the fact that these folks who didn't know networking were trying to build a network that never existed before. So that's the two sides on the positive. On the flip side, the networking industry as a whole, if I may, hasn't really been big on software. There aren't a lot of software engineers working at many networking companies. So now when you say, I'm going to take classic problems in leader election and consensus and high-performance distributed computing and apply them to networking, it takes a substantial DNA shift, and one that through just luck and happenstance, Google was in a better position to affect, given the DNA of the company.
All right, one last question over there.
So, I mean, I want to take you back to thoughts on Dave and a particular term maybe we didn't hear enough of, which was persistence. So, if I can take you back to a paper called WebOS. This, I guess, a few years ago received the 25-year test of time from HPDC, and I think that was maybe the 5th place we submitted the paper. Thoughts on persistence? Did we have it right? From listening to your talk, it sounds like we were close, but we didn't go far enough back then.
So in that paper, we had section 7 called Rent a Server in 1996 when we started writing that paper. And the idea behind Rent a Server, I see Mike Delane in the audience as well, was, hey, wouldn't it be great if you could transparently access computing power across the internet on demand and install your computation on it? Yeah, we had the paper soundly rejected multiple times. And the part that you might have forgotten, David, is actually it was never accepted to HPDC. The program chair invited the paper after the So, you know, I went on the job market without any first authored papers. And so I know failure probably as well as most people in the audience. So I think persistence is probably another really important trait that I learned at Berkeley from Dave, from all the great colleagues around me. Thank you for the question.